So before we go on to the ratio test, I wanted to do a little bit of a reminder slash introduction to the factorial in case any of you haven't dealt with it for a while or haven't dealt with it at all. So strictly speaking, a factorial is a way to write out a product of large numbers of consecutive integers. So, for example, say 5 times 4 times 3 times 2 times 1, this is what we would call 5 factorial. Right? So the factorial always stands for the product of numbers from that number all the way down to 0, or sorry, all the way down to 1. Okay? And it always sort of, we can only use this on whole numbers. Right? There's ways to sort of extend the definition of the factorial, but we're not really going to touch on that here. So, right, so generally speaking, the factorial, n factorial, right, where n is some integer greater than or equal to 1, this will be 1 times 2 times 3 times ... times n minus 1 times n. Right, so we're multiplying all the numbers up to n. Right? Now, some special things. A special case is that 0 factorial is equal to 1. Right, so there's a reason for this definition. One, because it makes sense, sort of, it works for consistency for us. But like I said earlier, there's a way to extend the factorial. And it turns out that 0 factorial has to be 1. Right? So I won't sort of, again, get into the details of that, but if you're curious, look up something called the gamma function. Anyway, one particularly useful thing about the factorial is how it cancels out. So let's say we had the numbers, just 5 times 6 times 7. Right? Let's say we had something like this, right? This is a product of consecutive integers, but it doesn't start at 1. What we can do then is say, well, what if I add in the stuff that I'm missing, 1, 2, 3, and 4, but then divide by that extra stuff? Right? So really, this gives me 7 factorial over 4 factorial, which is kind of neat. Right? So we can always get these sort of products of consecutive integers as quotients of factorials. Right? So likewise, you might see something like, I don't know, maybe you're given 10 factorial over, 7 factorial, let's say. Right? So if you're ever given something like this, and things like this can pop up, you can just say, well, to compute this, I know this is the numbers 1 through 7. This is the numbers 1 through 10. So the only thing that's going to be left over after this quotient is everything past 7. So this will be 8 times 9. It's 10. Right? So again, these factorials are a good way to condense a lot of this, these kind of products like this that will show up. Right? So, let's say you had something like, to write a more general one, maybe you had something like 2k factorial. You want to make sure to get that 2k in parentheses there, divided by k factorial. Right? So I'm not specifying what k is, but I want it to look somewhat generic. Right? So this is all the numbers from 1 through 2k. This is all the numbers from 1 through k. So what's going to be left over is, well, actually, let's write it out so we can see what's left over. So here we have 1 times 2 times ... times, now I'm going to write a couple extra things in here. K minus 1 times k plus 1 ... through 2k. Right? And then on the bottom here, I have 1 times 2 times ... times k minus 1 times k, and that's it. Right? So all of this stuff cancels all of that part, but it leaves the rest of this out there. Right? So what's left over here is k plus 1 dot 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 through 2k. Right? So we multiply everything from k plus 1 onward. So again, the idea is when we have a quotient of factorials like this, you say, all right, well, which one is the larger number? 2k is larger here. So, we say, all right, everything up to k in this product, get rid of it, and then just take the leftovers there. Right? One interesting thing I want to point out is in terms of, how these numbers grow, right? So we know something like, let's say we had, what's a good way to do this? Let's say we have k to some power, p. We know that grows slower than p to the kth power, right? A polynomial grows slower than an exponential function. Actually, maybe instead of using, we'll use k. Right, and we know polynomials are faster than, say, logarithms, for example. But what we also know is that factorials are actually much, much faster than exponential functions, right? Because an exponential function just multiplies the same number over and over and over. But I guess here maybe I should emphasize for large values of k. An exponential function just multiplies the same value p over and over and over and over and over. Whereas a factorial will eventually start multiplying larger and larger and larger and larger numbers. Right? So just wanted to give you that little primer on the factorial in case you have or have not seen it before, because this is going to come up in all the stuff we're going to be doing from now on.